Welcome to the electronicshobbyblog.com. I'm your host, Dominic Soldano, and today we've got a new project on the bench. I've been wanting to get some LED photo lights. Right now I've got old tungsten lights and they get pretty hot and they use quite a bit of power. And so I thought, I wonder how cheaply I can build an LED photo panel. And so I ordered some LEDs on Amazon. I ordered 100 each of cool white and warm white, and ended up paying about $14 for the 200 delivered. Other than that, I'm only going to use parts that I currently have laying around, including some of those 12-volt wall power supplies that I have left over from the Raspberry Pi in a tower case project. So stick around and we'll see how to build this LED photo panel. Let's start by looking at the requirements. First, we'd like to be able to adjust the color temperature between daylight, or around 3200 Kelvin, and incandescent light, or about 5600 Kelvin. To do that, we'll be using two types of LEDs, cool white and warm white. Next, we'd like to be able to adjust the intensity between off and full, whatever that turns out to be for 173 LEDs. In addition, I want to make maximum use of parts that I already have, including those 12-volt wall supplies that are left over from the Raspberry Pi project. Here's the specs on the LEDs we'll be using. Both of them are rated at 3.2 volts and 20 milliamps per LED. I did some testing in the lab and found out that the cool white LEDs come in pretty close to the spec, but the warm white LEDs are closer to 3 volts, and we'll need to take that into account for our design. Since we're using a 12-volt supply and the warm white LEDs take about 3 volts per, we can put 4 of those in series, and that'll add up to our 12 volts very nicely. I tried putting 4 of the cool white LEDs in series as well, but because they have a higher voltage requirement, they didn't get to full brightness. So I'll use them in strings of 3. Now that still leaves us 2.4 volts that we've got to drop so we don't burn out the LEDs. To do that, we'll use a technique that we learned in our last lesson on diodes. Remember that the voltage drop across a diode is fairly constant over a wide range of currents, and that'll come in really handy here. So for these 1N4001 diodes that I've got, the voltage drop is about 0.8 volts per diode. So putting 3 of those in series will give us that 2.4 volt drop over the wide range of currents that we can expect as we dial the intensity up and down. With that worked out, I started construction on the board. For the cool white LEDs, there'll be 8 rows of 12 LEDs. I spaced them apart so that I could fit the warm white LEDs in the gaps in the matrix. So essentially in the center of every 4 cool white LEDs. So for the warm white LEDs, there'll be 7 rows of 11 LEDs each. I started by applying a small bit of solder to one of the leads. Then I pressed on the LED and held it tightly into place when I reheated the solder so that it would sit flat against the board. Once that was done, I soldered the second lead into place. After that, I began installing additional LEDs and soldering them into place using the same technique. In between each set of LEDs that I soldered in, I checked to make sure that everything was nice and snug against the board and that it sat straight and true. When you're doing this, it's important to make sure that you have all the anodes and cathodes facing the right direction, especially because of how we're going to wire it up. Once a group of 3 was soldered in place, I bent the leads over so that they would lay cathode to anode and cathode to anode, and then soldered the cathodes and anodes together so that I got a string of 3 with an anode on one end and a cathode on the other. Then I did the same thing for the next group. And the next group, and the next group, and the next group. After I completed one row, I started on the next row and kept doing row after row after row until I'd finished it. I gotta tell you, this was tedious work, and your eyes start to bug out after a while. At a certain point, I started to connect all of the anodes and cathodes together so that I would end up with a bunch of groups of 3 in parallel. And then later, I could wire each set of columns so that everything was in parallel. Eventually, I ended up with a matrix that was a whole bunch of sets of 3s connected in parallel. And here's what it looked like when I hooked it up to 12 volts. It may not look it in the picture, but it's pretty bright. After I finished with the cool white LEDs, I started to put the warm white LEDs into each gap in the matrix. At this point, I found it easier to just do a whole row of LEDs at a time. Insert them, and then solder them in place before bending the leads to connect them together. Again, this was pretty tedious work, so I did it over a couple of days' time. I just couldn't sit there and stare at the board under the bright lights. I just couldn't get my eyes to focus on the board for more than an hour at a time. I used the same technique as previously, soldering one lead into place and then making sure all of the LEDs sat nice and flat against the board before soldering the second lead. Once again, it's important to make sure that all of the anodes and cathodes are facing in the same direction. The technique I used to solder these together was quite different because I already had the anodes and cathodes from the cool white LEDs running up and down. So what I did was I bent each one so that it formed a loop above the previous leads. Here's a close-up of what that looked like. Sorry if it's a little blurry in the bottom, but you get the idea. Because there were only 11 in each row, and it wasn't a number that was divisible by 4 or 3, I had to get a little creative with the connections. I continued doing that for each row. Eventually, I finished, and I turned my attention toward the circuit that would control both the color temperature and the brightness. We're going to use MOSFETs to control our LED panel. Each group of LEDs, the warm white and the cool white, will draw about 450 milliamps. So we need something that can handle the current. The MOSFET is perfect for that. In experimenting with the MOSFETs and a few of the LEDs, I found out that they come on when the gate voltage of the MOSFET reaches 1.2 volts. And they're at full brightness based on the current draw when the gate of the MOSFET is at 2.1 volts. The first part of the circuit, shown on the left, is a voltage divider controlled by a 10K potentiometer that allows the voltage to adjust between 3.3 volts and 8.1 volts. This feeds into another voltage divider, but in this case, turning the pot one way causes one side of the voltage divider to vary between 1.2 and 2.1, while the other side varies between 2.1 and 1.2. Essentially, as one of the points goes up, the other goes down. This is how we'll vary the voltage back and forth between the cool white and warm white LEDs. As we turn the potentiometer in one direction, the voltage at the gate of the MOSFET that's controlling the warm white LEDs increases, while the voltage at the gate of the MOSFET that's controlling the cool white LEDs decreases. So as one goes up, the other goes down, and we can vary the amount of each. While I'm only showing the matrix for the cool white LEDs, along with its associated MOSFET controller, that same MOSFET configuration, along with the matrix, is repeated for the warm white LEDs. Basically, the portion to the right is repeated for both the cool and white LED matrices. Here's an early prototype of that circuit in the lab with just a few LEDs. The potentiometer I'm adjusting here controls the overall brightness. That's that voltage divider circuit that was on the left. And here I'm adjusting the potentiometer that changes the split between cool white and warm white. You can see as I turn one up and then the other goes down and vice versa. I wasn't too happy with the way this worked. I didn't think that it gave me the full power of all the LEDs. I didn't get quite the level of adjustment I wanted between cool white and warm white. And here's another view of that same circuit. It's a little easier to see from the side because you're not being blinded by the LEDs. Like I said, they're pretty bright. Here's my second design concept. In this case, each string of LEDs is controlled by a separate potentiometer. So that lets me get the full range out of both the cool whites and the warm whites. And here's that second circuit in the lab. I was a lot happier with the level of control I could get out of this because I could control each portion of the matrix separately. Both could be full on, both could be 50% on, both could be off, both could be 25% on, one could be 25%, one could be 75%. You get the picture. It was also fairly easy to adjust. So far I'm leaning toward this concept, but there might be a few more I want to try. One concept that I find intriguing would be to use a microcontroller like the ATmega 328 that's found in the Arduino to control each of the MOSFETs independently. That way you can have one dial for color temperature and one dial for intensity, and you can use a lookup table to adjust them appropriately. I may give that a try. And here you'll get some idea of how the current varies as we make adjustments. We're set at 12.1 volts because that's what I measure at the output of our wall power supply. That should represent the actual operating condition. Well, I hope you enjoyed that. So please give me a thumbs up and go ahead and subscribe so you won't miss part 2 where we finish the control circuit and test it. Until then, cheers and happy Thanksgiving.